Hi, in the video about ozone in the atmosphere, I showed a graph of a radiative forcing from different gases, like this one. The star shows the F gases, the fluorinated gases, and they're virtually all unnatural in the atmosphere, but are products from our lifestyles: refrigerants, aerosol propellants, foamed plastics. They are also used in the manufacture of processes which require very unreactive environments. These are all very useful in our lifestyles, but the gases have become increasingly noticeable components in our atmosphere over the last generation. The F gases include CFCs, the chlorofluorocarbons, and one example is listed here, the CFC11, that is CFCl3, and another CFC12, CF2Cl2. The effects of these gases were first noticed in the stratosphere, a layer of the atmosphere above the normal weather. Ozone molecules can absorb high ultraviolet light, and as a result of that, the ozone molecule is split into an oxygen molecule and an oxygen atom. When an ozone hole is identified in the poles, it's because the concentration in the stratosphere is relatively low, allowing more of the damaging UV radiation to reach the surface, and that can cause tissue damage. This was very evident in the 1980s over the Antarctic in particular, and the main cause for this was pinned down to chlorine atoms produced by the effect of high energy light from the sun degrading CFCs, which act as ozone depleters. The chlorine atoms react with ozone to form chlorine oxide and oxygen, O2. ClO itself reacts with an oxygen atom which might otherwise go on to create an ozone molecule, but instead this becomes another O2. And the killer is the fact the effect of the chlorine is catalytic. The first step is used, but in the second it is reformed. The ClO does not appear in the overall reaction, so chloride can go on to repeat this exercise many times, and so is very destructive. The seriousness of this for human health was a great instigator in arriving at the International Convention, the Montreal Protocol, which was finalized in 1987. The agreement was to a pathway to phase out ozone-depleting substances, or ODSs. As a result, substitutes without chlorine were introduced, and the benefit of the stratospheric ozone was apparent, but the emissions of fluorinated gases have increased greatly since the Montreal Protocol. What has this done with respect to the greenhouse effects? The infrared spectra of these molecules contain some very strong absorptions. The carbon-chlorine stretches are close to the maximum output energy of the infrared radiation from the Earth's surface, and the carbon-fluorine ones just slightly higher. So the Montreal Protocol did diminish output of the molecules absorbing in the CCl region, but kept those with the carbon-fluorine bonds. The effect on the measured values of radiative forcing is also evident. In the early 1990s, the RF or CFC11, which has a residence time of about 45 years, passed through a maximum. The residence time of CFC12 is longer, 100 years, but it too reached a maximum in the 2000s. The residence time of a gas in the atmosphere is very important. A combination of the property of the molecule, the radiative efficiency, and its lifetime contribute to its global warming potential, or GWP. This will vary with time after the emission, and two time periods are widely used as 20 and 100 years. Each is compared to CO2 given the value of 1. Excess CO2 lasts for hundreds of years and so will tend to accumulate for a very long time. Methane has a relatively short lifetime, so the GWP reduces relatively with time, but after 100 years of emission, it is still much higher per molecule than that of CO2. CFC12 carries a big punch and has a similar resonance to CO2. We want really to avoid further release. We can see that replacement of chlorine by fluorine, as in CF4, can reduce the GWP, but relative to CO2, this increases with time, implying a very long residence time. This has only been estimated, but at 50,000 years. The carbon-fluorine bonds are extremely stable. With slightly longer chain molecules like perfluoropropane, the residence time decreases, but still is over 2,000 years. Perfluorocarbons, PFCs, are not viable substitutes for CFCs because of this detrimental effect on global warming. The CH bonds provide different degradation mechanisms, and the lifetimes of these hydrofluorocarbons, HFCs, are significantly reduced, more like those of methane. These are now widely used, so when one scenario for a target of 1.5 degrees C temperature rise by 2100, which is termed RCP 2.6, when it was drawn up, it allowed for increased emissions of these HFCs. But these compounds each have values of GWP of thousands of times larger than CO2, and so they too should be replaced. A further generation has been the hydrofluoroolefins Hfos. These have two less atoms on the carbon backbone, creating a carbon-carbon double bond. This greatly reduces the lifetime in the atmosphere, and as a result the GWT factors are much less than 1, and so on that criterion less polluting than CO2. But what happens to the molecule after it is degraded in the air? The evidence is that it reacts with oxygen, and the stable CF3 residue is attached to a formyl group. This contains a CO unit, and it has just been reported that this loses a carbon monoxide molecule on photolysis, resulting in fluoroform. This is otherwise known as HFC33 and has a lifetime in the atmosphere of about 270 years. The photo products are really bad news. It was good that the USA announced this week to achieve very high reductions in HFC emissions. The comment from Carbon Brief that it would have been more impressive if the EPA had also announced the substitutes. But the targets can focus the mind. And indeed, the EU's F-gas directive already has done that. The proposed substitutes must be evaluated only once the photochemistry is known. It may be challenging to find planet-safe refrigerants that are close matches to present-day devices. For some uses, CO2 itself is viable, and it would be much less damaging than the current fluorine-containing fluids. Once in the atmosphere, they stay there a long time. The effect on the headroom for global warming is a bit like having a large rock inside a swimming pool. There is much less room for the water, and swimming is more hazardous. In the long haul, it would be great to chip away at this rock by CFC, PFC and HFC capture and storage and/or conversion. But this will be hard. The gases are very dilute once they have escaped, and the molecules are Teflon-like. It would take some clever shape selection to capture them. Perhaps for some uses we may turn to the thermoelectric cooling, the Peltier effect, and also await a breakthrough in magnetic cooling. Even now we can be careful with our own toiletries, sprays, and refrigeration systems, including heat pumps, both what we purchase and how we dispose of them. We should also have a sharp focus on the proposals of countries and agreements at COP26 on this important problem.